At a recent celebration, you may have seen fireworks. The fireworks display of color and sound was the result of chemical reactions. Chemical reactions constantly take place all around you, though many are less dramatic than fireworks exploding. A car rusting in a field, the hardening of concrete at a construction site, and the digestion of food inside the human body are all examples of chemical reactions. The careful, systematic study of what happens during chemical reactions has provided chemists with much of their knowledge about chemistry. This program shows how to balance chemical equations, such as the one for the reaction of potassium, metal, and water. Knowing how to balance equations is a valuable skill that will help you understand chemical reactions. You will be shown a classification system that describes several types of reactions. Before exploring chemical reactions, the program will start with a definition of terms that will be used, a brief review of compounds, and an overview of solutions. A chemical reaction occurs when one or more substances are converted into new substances having different chemical and physical properties. For example, when a car rusts, iron and oxygen combine and form iron 3 oxide. The substances present at the start of a reaction are called reactants. In the rusting car example, iron and oxygen are the reactants. The substances that result from a chemical reaction are called the products. In the previous example, the product is iron 3 oxide. In a chemical reaction, reactants are converted into products. A balanced chemical equation provides a shorthand method for representing the number and types of atoms involved in a reaction. The following scenes provide a brief review of chemical bonds and the nature of ions. There are two different types of bonds in various chemical compounds: covalent and ionic. Covalent bonds result from the sharing of electrons between atoms. The sharing of electrons in covalent bonds creates molecules. A molecule is a collection of covalently bonded atoms that behaves as a unit, such as the water molecule. As anyone who has seen the ocean is aware, bodies of water can be quite large, but each water molecule is a discrete entity with specific hydrogen atoms attached to a specific oxygen atom. Because of this, molecules are represented by molecular formulas, in which the symbol of each element in the molecule is followed by a subscript indicating how many atoms of that element are in the molecule. No subscript after an element symbol indicates that just one atom of that element is present in each molecule. For example, water is H2O because 2 hydrogen atoms and 1 oxygen atom are covalently bonded. Hydrogen peroxide is a molecule in which 2 hydrogen atoms and 2 oxygen atoms are covalently bonded and thus is symbolized H2O2. Ionic bonds form from the attraction among oppositely charged ions. Ions are atoms or groups of atoms that have lost or gained electrons and thus taken on a positive or negative charge. An atom is electrically neutral because it has as many electrons surrounding the nucleus as protons in the nucleus. Since electrons are negatively charged, gaining electrons gives an ion a negative charge. For the same reason, losing electrons gives the ion a positive charge, because there are less negative charges to balance the positive charges of the nucleus. The charge on an ion equals the number of electrons it has gained or lost. A superscript placed after an ion symbol indicates the magnitude of the charge and its sign, either positive or negative. For example, magnesium tends to lose 2 electrons, forming the Mg2+ ion. Ions possessing a single charge are indicated by the appropriate sign for positive or negative, and the number 1 is implied and not written. This is illustrated by chlorine, which tends to gain 1 electron, forming the chloride ion Cl-. The elements on the left side of the periodic table, known as the metals, tend to lose electrons and form cations. A cation is an ion with a positive charge. The elements to the right side of the periodic table, the nonmetals, tend to accept electrons, becoming negatively charged. A negative ion is known as an anion. A group of atoms covalently bonded together that possesses a charge is called a polyatomic ion. Examples of polyatomic ions are carbonate, sulfate, and ammonium ions. In chemical reactions, polyatomic ions tend to act as single units. This means that in many reactions they are not broken up and rearranged and are present in the same grouping in the products and the reactants. For example, when sodium sulfate and cesium carbonate react, the polyatomic sulfate ion is transferred from sodium to cesium, and the polyatomic carbonate ion switches from cesium to sodium. In both cases, each polyatomic ion makes the switch as an intact group. Knowing which charges individual elements assume when they form ions is important when balancing equations of chemical reactions. You may have already learned that an atom tends to form an ion or covalent bond that gives it 8 electrons in its valence shell or outermost shell of electrons. This is known as the Octet Rule. The representative elements are the elements in group 1A through 8A on the periodic table. Each representative element tends to form an ion with an octet by gaining or losing the number of electrons that gives them the electron configuration of the noble gas nearest in atomic number. The noble gases are the elements in group 8A, which have filled valence shells. Since each noble gas has an octet, there is nothing driving it to gain, lose, or share electrons, and therefore they tend not to react or form ions. The oxygen atom, which has 6 electrons in its valence shell, achieves an octet by gaining 2 electrons. This means that the resulting oxide ion has a charge of -2 due to the negative charge on each of the 2 extra electrons. The sodium atom only loses 1 electron to achieve an octet. Therefore, the sodium ion has a +1 charge. The charges formed in elements 1b through 8b are not as predictable, and many have more than one ionic state. The stock system of naming ions shows the oxidation number of elements that can form more than one type of ion. While oxidation number is a complex subject, for the purposes of this program, oxidation number is equal to the charge on an ion. When using the stock system, the Roman numeral following the name of an element gives the number of the charge, for example, iron 2 and iron 3. The stock system is only used with elements that commonly form more than one ion. Unlike covalent bonds, which were discussed earlier and result from a sharing of electrons, ionic bonds are formed when atoms or groups of atoms lose electrons to other atoms or groups of atoms. The opposite electrical charges of the ions formed lead to the attraction that forms the ionic bond. Ionic compounds are electrically neutral because the number of positive charges equals the number of negative charges. When they are in the solid phase, ionic compounds exist as repeating units of cations and anions, forming what is known as a crystal lattice. The nature of the crystal lattice means that most ionic compounds do not exist in discrete units like covalently bonded molecules do. For example, a chlorine atom in a diatomic chlorine molecule is covalently bonded to another specific chlorine atom, forming a discrete unit. But a chloride anion in a sodium chloride lattice is equally attracted to all of its neighboring sodium cations by ionic bonds. Ionic compounds are represented by formula units, the smallest whole number ratios of each ion in the compound. For example, the formula unit for calcium oxide is CaO, because there are equal amounts of calcium cations and oxide anions. The formula unit for barium chloride is BaCl2, because there are twice as many chloride anions as there are barium cations within the crystal lattice. Notice that the cation is named first in a formula unit. The subscript in a formula unit indicates how many ions of that element are present per formula unit. As in molecular formulas, lack of a subscript indicates there is one ion in each formula unit. In neither of these examples is there a charge on the formula unit. This is because the charges of all the cations and anions in a formula unit will always cancel, leading to electrical neutrality. For example, in barium chloride, the single negative charges of each of the two chloride anions cancel the two positive charges of the barium cation. In a chemical reaction between ionic compounds, cations and anions are exchanged between reactants in the appropriate proportions to lead to electrical neutrality. This means that when writing the formula unit for an ionic product or reactant, the charges present on the anions in the compound must cancel the charges on the cations. If you are only given the name of the compound, you can determine the formula by using what is known as the Crisscross Method. What is the formula for iron 3 oxide? First, look at the charges on the cation and anion. When compounds are named using the stock system, as they will be throughout the program, the number in parentheses is equal to the charge on the ion. Since the cation is always named first in the formula unit, you know that iron has formed an ion with a +3 charge. Earlier you learned how to determine that the oxide ion has a charge of -2 by looking at the periodic table. To determine the formula unit, crisscross the absolute value of the charge of the anion to the subscript position of the cation, and the absolute value of the charge of the cation to the subscript position of the anion. Then reduce the subscripts to their lowest whole number ratio. Since the subscripts in this case are 3 and 2, they are already in the lowest ratio. In the lab, many reactions are performed in solution, so it is important to have a basic understanding of the properties of solutions. Solutions can exist in any combination of solid, liquid, and gas, a few examples of which are shown on your screen. A solution is a homogeneous mixture of more than one substance. To say a solution is homogeneous means it is uniform throughout, and a sample taken anywhere in the solution will be chemically identical to a sample taken anywhere else in the solution. While solutions can exist as solids, liquids, or gases, in the lab, solutions are generally liquids or gases. A solvent is the substance into which other substances, called solutes, dissolve. Water is a very common solvent both in everyday life and in the lab. The measure of the amount of a substance that goes into solution is called its solubility. Solubility differs for each combination of solvent and solute and also varies with increasing temperature. If a substance such as sand will not go into solution, it is termed insoluble. Salad oil is insoluble in water, which is demonstrated by the fact that the two liquids do not mix and the oil floats on the water's surface. To illustrate why solutions are often used in the study of reactions, look at a common example of a solution, dissolved table salt in water. Once the salt is stirred into solution, there's a uniform distribution of the solute, salt, which breaks up into sodium ions and chloride ions in solution throughout the solvent, which is water. The reason that liquid solutions and gases are used so often to perform reactions is that the reactants are brought into contact much more frequently in these states than they are in solids. This is because molecules and ions in solution move faster and farther than those in a solid. As you will learn when you study reaction rates later in your chemistry studies, bringing reactants together more frequently greatly increases how quickly a reaction occurs, and faster reactions are more often practical to study than slower reactions. Solutions in which water is the solvent are known as aqueous solutions. When an ionic compound dissolves into aqueous solution, the cation and the anion separate from each other. This process of separation is called dissociation and results in separated ions moving freely throughout the solution. Ions that have undergone dissociation are said to be dissociated. Although there are many charged particles in the solvent, the solution has no net charge because the positive and negative charges balance just as they did in the crystal lattice prior to dissociation. The separation of ions in solution makes them much more available to react than they would be if they were in a solid. Separated ions conduct an electrical current in solution as they move toward the electrode of opposite charge. Pure water does not conduct electricity well, so it's possible to tell if a compound has dissociated by determining if a current flows through the solution. The separated ions are known as electrolytes. If a current is conducted in aqueous solution, the compound has dissociated to form electrolytes. Some molecular substances also form solutions in water. Many, such as table sugar, dissolve in water but do not undergo dissociation. They do not conduct electricity through water and therefore are not electrolytes. The reason that sugar goes into aqueous solution is related to the polarity of sugar molecules and water molecules, which will not be discussed in this program. Other molecules, especially molecular acids and bases, do dissociate in water and produce ions, and are consequently electrolytes. As in the previous scene, the separation of ions increases the ability of the aqueous solution to react, making it easier to study. To understand how chemical reactions take place, it is necessary to have a thorough understanding of chemical equations. Chemical equations are a shorthand way of describing both the composition and amounts of all reactants and products. A common example of a chemical reaction occurs when hydrogen gas and oxygen gas combine to form water. When this balloon, which is filled with hydrogen gas, is ignited, it reacts with oxygen in the atmosphere to produce water vapor, heat, and light. In this case, hydrogen and oxygen are the reactants, and water is the product. We can make an equation that states in words what is happening. Hydrogen plus oxygen yields water. This is known as a word equation. While a word equation is an accurate statement, it has some drawbacks. First, it is not a universal statement. A French chemist would not necessarily understand the meaning of these English words. Second, a word equation is a qualitative statement, but not a quantitative one. This means that the statement tells us in broad terms what is happening, but it does not tell us how much of each substance is involved. In the next scenes, you will see what chemists have done to solve these problems. The first problem with word equations is their lack of universality. Chemists have surmounted the language barrier by creating chemical symbols for each of the elements, such as H for hydrogen and O for oxygen. In addition, chemists have developed a system of nomenclature that allows each substance to be represented by a formula. This can be a molecular formula or a formula unit. For example, the word water might not make sense to a French chemist, but the molecular formula H2O would be instantly recognizable. The chemist would immediately know that a water molecule consists of 2 atoms of hydrogen and 1 atom of oxygen. If you need more information on chemical formulas, consult a textbook. The other problem with word equations is that they are not mathematical statements. From the statement, hydrogen plus oxygen yields water, there's no way of telling how many atoms of hydrogen and oxygen are involved. The law of conservation of matter states that matter can be neither created nor destroyed. Atomic theory says that atoms maintain their identities in a chemical reaction. Taken together, these statements mean that any equation for a reaction must balance, meaning there must be as many atoms of each element on the product side as there are on the reactant side. Therefore, all of the atoms on both sides of the equation must be accounted for. The next few scenes will show you techniques for balancing equations and accounting for the atoms involved in chemical reactions. The first step in balancing a chemical equation is to replace the names of the compounds with their correct chemical formulas. Using the formulas for molecular hydrogen, molecular oxygen, and water leads to the following equation. H2 plus O2 yields H2O. A quick look at this equation will show you that this is not a balanced equation. Do you see why not? While there are 2 atoms of hydrogen on both sides of the equation, there are 2 atoms of oxygen on the left side and only 1 atom on the right side. This means that 1 atom of oxygen is unaccounted for. Since matter is always conserved, this is an unacceptable situation. Fortunately, however, a method has been developed to reconcile this and balance the equation. Perhaps it has occurred to you that the equation can be balanced if the subscript is removed from the oxygen molecule. This may be tempting, but it is not an acceptable way to balance equations because changing the subscripts of a substance changes the nature of the substance. For example, removing 1 oxygen atom from the relatively non-toxic carbon dioxide molecule leads to the highly toxic carbon monoxide molecule. In a way, it would be analogous to replacing a bicycle with a unicycle. Though a unicycle has half the number of wheels a bicycle has, that does not make it half a bicycle. Each has its own unique character. Molecular oxygen consists of 2 atoms of oxygen and must be treated that way in the equation. Instead of changing the subscript, how about multiplying the amount of products or reactants? This is an acceptable way to manipulate an equation because only the amount of the substance changes, not its essential nature. In the example of water formation, 2 atoms of oxygen are needed on the right to balance the 2 atoms of oxygen on the left. This increase in the number of oxygen atoms can be achieved by doubling the number of water molecules. A whole number that precedes a chemical formula and tells how many units of the substance are present is called a coefficient. Therefore, the coefficient 2 is placed in front of H2O. When there are 2 molecules of water on the right, this means there are 2 atoms of oxygen on the right side because there is 1 atom of oxygen in each water molecule. This gives the equation H2 plus O2 yields 2 H2O. This equation is currently balanced with respect to oxygen atoms, but not for hydrogen atoms. The next scene continues the process of balancing this equation. Take another look at the equation from the last scene. Does this represent a balanced equation? There are 2 atoms of hydrogen in each water molecule, and there are 2 water molecules, so there are 4 hydrogen atoms on the right side. Since there are only 2 atoms of hydrogen on the left side, the equation is not yet balanced. Do you see a way to get 4 atoms of hydrogen on the left side? If you said placing the coefficient 2 in front of the hydrogen molecule could do it, you are correct. This gives the equation 2H2 plus O2 yields 2H2O. This is a balanced equation. There are 4 hydrogen atoms and 2 oxygen atoms on each side of the equation. In the last few scenes, you have learned techniques for balancing equations. The following rules summarize these techniques and add some refinements and strategies. The first step in balancing equations is to write a preliminary, unbalanced equation using the correct chemical formulas. The second step is to adjust the coefficients of the reactants and products until the equation balances. A polyatomic ion, such as the sulfide ion or the nitrate ion, frequently goes through reactions unchanged and can be treated as a unit when balancing equations. It is often easiest to begin balancing with elements or polyatomic ions found in only one reactant and one product. If the number of atoms of an element on the reactant side does not evenly divide the number of atoms of that element on the product side, it is often possible to use a variation of the Crisscross Rule. In this case, use the subscript of the element in the product as a coefficient for the reactant, and vice versa, then finish balancing as you normally would. Learning to balance equations requires a certain amount of trial and error and becomes easier with practice. The third step in balancing equations is to confirm the number of atoms of each element balances. Finally, make sure the coefficients are in their smallest whole number ratio. In the example on the screen, the coefficients are not in their lowest whole number ratio because they are all evenly divisible by 2. In addition to atomic symbols, subscripts, and coefficients, other symbols are frequently added to chemical equations. These symbols are used to provide more information about the reaction. For example, the physical states of the reactants and products are often noted. Placing the first letter of the name of the state, S for solid, L for liquid, or G for gas, in parentheses after chemical formula denotes the physical state of the substance. If the compound is in a solution of water, an AQ for aqueous solution is placed in parentheses. Here are examples using the equations shown earlier. Arrows pointing in both directions indicate that the reaction is reversible. That is, that it will proceed in both directions, from reactants to products and back to reactants. An uppercase Greek delta symbol above the arrow indicates that heat is being supplied to the reaction. An example is sodium bicarbonate being heated to form sodium carbonate, water, and carbon dioxide. If a chemical symbol appears above the arrow, it indicates that the compound or element acts as a catalyst, which is a substance that speeds up a reaction and is present in the same form before and after the reaction. Millions of different chemical reactions are constantly going on all around you. Does this mean that to understand chemistry, you have to memorize millions of reactions? Thankfully, the answer is no. By studying the way reactions occur, chemists have been able to classify many of them. In the remainder of this program, you will learn 5 common reaction types. Not every chemical reaction fits into one of these 5 patterns, and some of them fit in more than one. However, most of the reactions you encounter in your chemistry studies will fit into one of the patterns. The 5 reaction types are combination, decomposition, single replacement, double replacement, and combustion. Each type will be presented separately, starting with the combination reaction. You have already seen that iron combines with oxygen to produce rust, or iron oxide. In a combination or synthesis reaction, 2 or more reactants combine to produce one product. The general form of a combination reaction is X plus Y yields XY. The reactants in a combination reaction can be either elements or compounds. Because the product of a combination reaction is always more complex than the reactants, it will always be a compound. Earlier in the program, you saw a combination reaction in which both reactants were molecules. Recall that hydrogen and oxygen combined to form water. In 1937, this reaction took place with frightening force when the airship Hindenburg, which was filled with hydrogen gas, exploded over New Jersey. The hydrogen gas in the blimp reacted with atmospheric oxygen to form water and a great deal of energy. To avoid such tragedies, modern blimps are filled with a non-reactive gas, helium. There are many common combination reactions. When a group A metal cation reacts with a non-metal, the product is an ionic compound. An example is the reaction that produces common table salt. Sodium metal reacts with chlorine gas, producing sodium chloride. Here are some more examples of non-metals reacting with group A metals. When transition metals, such as iron, combine with non-metals, or when two non-metals combine with each other, there is often more than one possible product. For example, iron and oxygen can form iron 2 oxide or iron 3 oxide. Compounds of nonmetals and oxygen, nonmetal oxides, often combine with water to produce acids which have a low pH. For example, carbon dioxide combines with water to produce carbonic acid. This reaction occurs in carbonated beverages such as soda pop. Metallic oxides combine with water to form bases which have a high pH, as when calcium oxide combines with water to yield calcium hydroxide. On the screen are some other examples of acid and base formation through combination reactions. A decomposition reaction is essentially the reverse of a combination reaction. In a decomposition reaction, one reactant breaks down into two or more products. The general form for a decomposition reaction is XY yields X plus Y. Electricity can be used to break water molecules apart. Notice that the word electricity is placed above the arrow to indicate current drives the reaction. This reaction is the reverse of the combination reaction studied earlier. Liquid water decomposes into hydrogen gas and oxygen gas. Ammonium dichromate decomposes into nitrogen gas, chromium 3 oxide, and water when ignited. In general, a source of energy must be provided for decomposition reactions to occur because the reactants are usually stable. A third kind of chemical reaction is called a single replacement reaction. These reactions are also known as single displacement reactions. In a single replacement reaction, one element takes the place of another element in a compound. Single replacement reactions have the general form AX plus B yields BX plus A. When a piece of metallic potassium is placed in a dish of water, a violent reaction occurs. Potassium displaces one of the hydrogen atoms in a water molecule, producing hydrogen gas and aqueous potassium hydroxide. In this case, potassium takes the place of one of the hydrogen atoms in a water molecule. A less dramatic single replacement reaction takes place when a strip of zinc metal is placed in a solution of copper sulfate. The zinc replaces the copper ion in the solution and forms zinc sulfate. The copper that is displaced is deposited on the zinc strip. What happens if the situation in the previous scene is reversed and a copper strip is placed in a solution of zinc sulfate? The answer is nothing will happen. There will be no reaction in this case because zinc can displace copper from a compound, but copper cannot displace zinc. In fact, chemists have experimentally determined which metals displace other metals. The results can be displayed on a chart showing the hierarchy of displacements. Any element in the chart displaces the elements below it and is displaced by the elements above it. This arrangement of metal elements is known as the activity series, and it shows the relative reactivity of each metal. Thus, you can see that lithium will displace any metal on the chart, and any metal will displace gold. You may have noticed that the element hydrogen is on the activity chart with the metals, even though hydrogen is not a metal. It is placed there because in this type of reaction, it is useful to consider whether a metal can displace hydrogen from water. The activity series can be used to predict the outcomes of reactions. For example, in the reaction demonstrated earlier, the displacement of copper and the formation of zinc sulfate could have been predicted. Because zinc is higher on the chart than copper, and thus you know it is more reactive. If you were to place a copper wire into a solution of silver nitrate, would the copper displace the silver? Looking at the activity series, you can see that it would. Silver would leave solution, plating on the wire, and aqueous copper 2 nitrate would form, giving the solution a bluish tint. What would happen if you placed silver in copper 2 nitrate solution? In this case, a look at the activity series tells you nothing would happen. Single replacement reactions also occur when non-metal elements displace other non-metal elements, just as some metals can displace other metals. For example, when chlorine gas is bubbled through a solution of sodium iodide, the chlorine displaces the iodine, yielding aqueous sodium chloride and solid iodine. Non-metals also show trends in displacement. With the exception of the non-reactive noble gases, non-metal elements on the right side of the periodic table or higher on the chart tend to displace those that are lower or on the left. Knowing this, would you expect sulfur to displace oxygen from zinc oxide? This reaction does not happen, which can be predicted by the fact sulfur is lower on the periodic table than oxygen. A fourth type of reaction is known as a double replacement reaction. Double replacement reactions have the general form AX plus BY yields BX plus AY. For example, if solutions of lead nitrate and potassium chloride are mixed, a white solid forms that settles to the bottom. The solid is lead chloride, and it is referred to as a precipitate. Precipitates are solids that form when solutes react and form insoluble products. The reaction in this case is a double replacement or double displacement reaction because an exchange of atoms or ions occurs between compounds. In this case, lead cations bond to chloride anions and precipitate out, and potassium cations and nitrate anions stay in solution. The reaction can be written like this. This way of representing a double replacement reaction is known as a molecular equation, although this is a bit of a misnomer since these equations represent not only molecular compounds, but also ionic compounds, as in the example. In a molecular equation, the formulas of the reacting solutes and the possible products are listed as compounds. In some cases, the product of a double replacement reaction is a gas, as when hydrochloric acid reacts with sodium sulfide. In this case, hydrogen sulfide gas is produced and bubbles out of a solution while sodium chloride remains in solution. Hydrogen sulfide gas has a characteristic rotten egg smell and is emitted by fumaroles, which are openings in volcanic areas. Sometimes the two solutions form a liquid, often water. This is the case in the reaction of sulfuric acid with aluminum hydroxide, which produces aluminum sulfate and water. This reaction is an example of an acid-base neutralization reaction, which you will learn more about as you continue studying chemistry. The water produced mixes with the solvent, which is also water, and the aluminum ions and sulfate ions stay in solution as indicated by the notation AQ. The ions that stay in solution are called spectator ions because they do not participate in the reaction. In the reaction that produced hydrogen sulfide, the sodium and chloride ions are spectator ions since they remain separated in the solution. In the other reaction, the aqueous aluminum sulfate exists as spectator ions because the ions remain separated in solution. Sometimes when solutions are mixed, no precipitate forms, no gas bubbles off, and no water or other liquid forms. If none of these things happens, then no reaction is considered to have occurred. This is because all of the cations and anions stay in solution. For example, when barium chloride and ammonium nitrate solutions are mixed, there is no net reaction and all the ions are spectator ions. The outcome of double replacement reactions can be predicted by looking at the possible combinations the ions in solution can make if they switch partners. If a product forms a gas, like hydrogen sulfide, that is not very soluble, it will tend to leave the solution. If water is formed, it can join the solvent. If a precipitate such as lead chloride forms, it will settle out of solution. If none of these events occurs, there is no driving force for a reaction and no reaction occurs. While it is easy to predict if a gas, water, or other molecular compound is formed, is it possible to predict whether an ionic compound will settle out of solution? Chemists have developed a set of solubility rules that will answer this question. Take another look at the reaction in which lead chloride precipitates out of a mixture of lead nitrate and potassium chloride solutions. Rule 4 on the solubility chart states that most chloride salts are soluble, with the exceptions of silver chloride, lead chloride, and mercury 1 chloride. Since lead chloride is one of the exceptions to the rule that chloride compounds are soluble, it will form a precipitate. The other possible product is potassium nitrate. As can be seen from Rule 1 and Rule 2 on the solubility chart, both nitrate salts and salts of group 1A metals are usually soluble, so these ions stay in solution as spectator ions. The solubility chart can be used to predict whether precipitates will form when solutions are mixed. If ammonium perchlorate and copper 2 nitrate solutions are mixed, what happens? The 4 ions that are in solution are the ammonium ion, the perchlorate ion, the copper 2 ion, and the nitrate ion. Since we already know that the reactants are in solution to start the reaction, we only have to check the solubility of the products. The possible products are ammonium nitrate and copper 2 perchlorate. Rule 2 on the solubility chart indicates that ammonium and nitrate ions will stay in solution and be spectator ions. Perchlorate ions are always soluble, so the copper 2 ions and perchlorate ions are also spectator ions, thus there are no precipitates formed. The reaction of lead nitrate and potassium chloride solutions was shown earlier in a molecular equation, which shows the possible recombination of ions, whether they are spectator ions or not. A reaction can be shown in an equation with the individual ions dissociated, which more accurately represents what happens in a double replacement reaction. This type of reaction is called a complete ionic equation. The reaction of lead nitrate and potassium chloride can be rewritten in complete ionic form as shown on the screen. Spectator ions are represented as separate ions. Notice that lead chloride is not represented as separate ions. This is because the ions form a precipitate and are no longer separated in solution. The complete ionic equation allows one to see all the ions involved in the reaction and any other products formed, such as precipitates or gases. When writing a complete ionic equation, make sure that you use the coefficients that accurately indicate the numbers of every ion involved. This can be done by multiplying the subscript of the ion by the coefficient of the substance from which it dissociated. For example, to determine the number of nitrate ions formed in solution by lead nitrate, multiply the coefficient of lead nitrate, which is 1, by the subscript of the nitrate ion, in this case 2. This yields 2 nitrate ions in the complete ionic equation. Sometimes one is interested in portraying only the reaction that actually occurs in the mixed solutions. In this case, a net ionic equation is used. A net ionic equation is a complete ionic equation with the spectator ions removed. Sticking with our previous example, the mixing of lead nitrate and potassium sulfate solutions, the net ionic equation is lead ions and chloride ions form solid lead chloride. As with the complete ionic equation, it is important to make sure that the ions have the correct coefficients. How about the net ionic equation for the mixing of ammonium perchlorate and copper 2 nitrate solutions? If all of the ions in this mixture remain in solution as spectator ions, how is a net ionic equation written? All of the spectator ions in a net equation are omitted, so in a case like this, it is indicated that no reaction occurs by simply writing no reaction. The following scenes give an example of how to write the molecular, complete ionic, and net ionic equations of a double replacement reaction. Solutions of cadmium chloride and sodium sulfide are mixed. First, write the balanced molecular equation by exchanging the cations and anions to form new compounds. What are the physical states of the reactants and products? By definition, the reactants are an aqueous solution, but what happens to the products? According to Rule 4 on the solubility table, most chlorides are soluble, so the sodium ion and the chloride ion are spectator ions, and sodium chloride is also in aqueous solution. By Rule 6 of the solubility chart, cadmium sulfide, which is used to color glass, is insoluble, and it will form a precipitate, as you see in the video. The next step is to construct a complete ionic equation for the reaction of cadmium chloride and sodium sulfide. Separating the ions, indicating the correct coefficients, and denoting the physical states gives the equation shown on the screen. Are the charges on both sides balanced as well? On the left side of the reaction, there are 4 positive charges and 4 negative charges, adding up to 0. On the right side, there are 2 positive charges and 2 negative charges, which also add up to 0. Thus, the complete ionic equation is balanced for charge. To construct the net ionic equation for the double replacement reaction of cadmium chloride and sodium sulfide, simply cancel out the spectator ions in the complete ionic equation. Doing this results in the equation cadmium ions plus sulfide ions yields cadmium sulfide. Again, only the ions that precipitate in a reaction and are no longer dissociated in the solvent are listed in the net ionic equation. Notice that the overall charge on the left side of the equation is 0, because the 2 positive charges cancel the 2 negative charges. The charge on the right side is also 0, because the product, cadmium sulfide, is a compound and therefore uncharged. The equation is balanced, and the charges on each side of the equation are equal. This gives you the molecular, complete ionic, and net ionic equations for the reaction of cadmium chloride and sodium sulfide. The 5th type of reaction covered in this program is the combustion reaction. Much of the energy used in your everyday life comes from the reaction of molecules with oxygen. Gasoline reacts with oxygen, and when burned, generates enough energy to power a car. Propane in a camp stove combines with oxygen to generate heat for cooking. The combining of a substance with oxygen, usually in a way that produces heat and light, is called combustion. Many important combustion reactions, such as those just mentioned, occur with organic molecules called hydrocarbons, which are made up of carbon and hydrogen. A simple combustion reaction occurs when methane is burned. Methane is the major component in natural gas, which is commonly used to heat homes. In the presence of abundant oxygen, and a source of ignition, methane will react with oxygen and produce carbon dioxide and water. Similar reactions occur with more complex hydrocarbon compounds, such as ethane, pentane, and octane. The combustion of the hydrocarbon acetylene and oxygen generates enough heat that it is used for cutting and welding steel. If hydrocarbon compounds burn in insufficient amounts of oxygen, carbon monoxide is formed instead of carbon dioxide. While carbon dioxide is relatively non-toxic and is generated by animals and used by plants, carbon monoxide is a poisonous gas, even at very low concentrations. For this reason, combustion reactions should always take place in a well-ventilated area. If, for example, wood, which reacts with oxygen like a hydrocarbon, is burned in a fireplace with a closed flue, the results could be tragic because the high concentration of carbon monoxide in the room could be fatal. When even less oxygen is present, the reaction produces elemental carbon, usually called soot. In the typical campfire, there are regions in which oxygen is abundant, restricted, or scarce, thus carbon dioxide, carbon monoxide, and soot are all produced. Carbohydrates are molecules associated with living organisms. In contrast to hydrocarbons, which contain only carbon and hydrogen atoms, carbohydrates contain carbon, hydrogen, and oxygen. Glucose and other sugars are carbohydrates, as are many more complex molecules. Carbohydrates react in the presence of plentiful oxygen in organisms to produce carbon dioxide and water, but the reaction occurs much more slowly than the burning of hydrocarbons. The reaction of carbohydrates with oxygen in organisms is called metabolism instead of combustion, although the products are the same. Fats and proteins are also metabolized in organisms, producing carbon dioxide and water and nitrogen compounds in the case of proteins. The metabolism of these compounds provides the energy necessary for the functioning, growth, and reproduction of most living organisms. If there is a reduced amount of oxygen available to the organism, less energy, along with potentially toxic products such as ethanol and lactic acid, are produced. This runner is feeling the effects of lactic acid buildup. Metals can also undergo a reaction with molecular oxygen. Magnesium metal reacts quickly with oxygen, as you can see in this demonstration. Pure magnesium metal is reacting with the oxygen in air, producing heat, light, and magnesium oxide. In most cases, the reactions of oxygen and metals are slower than this, do not generate light and heat, and are referred to as corrosion. The fact that corrosion and combustion reactions differ only in speed has led some people to refer to corrosion as a slow burn. Some products of slower combustion reactions are aluminum oxide and iron 3 oxide, or rust. Notice that these are also combination reactions. They are examples of reactions that can be classified in more than one way. This completes your introduction to chemical reactions. You've learned how to balance equations and write equations in the molecular, complete ionic, and net ionic forms. You have also learned about 5 types of reactions: combination, decomposition, single replacement, double replacement, and combustion. In addition, you have developed methods of predicting the outcomes of reactions by using the activity series or by determining the products of a double replacement reaction from the solubility chart. Understanding the various types of reactions and how to balance equations will be invaluable throughout your study of chemistry.